Welcome everyone, it's Berat again, and in this video we will be talking about Simon's algorithm. Alright, let's start. Well, in Simon's problem we're giving a binary function again, and it basically maps this like n long bit string to another bit string, okay? And we have said that this oracle function that implements this function, this binary function, is defined as fx is going to be equal to fy if and only if this x bit string is equal to y XOR with some s, some secret bit string that we do not know but want to find. Okay. Remember that this operation denotes the XOR operation, and for example, if our bit string is 0, 1, 1, when XOR with 1, 0, 1, you get 1, 1, 0. And how it happens is you XOR 1 with 0, you get 1. You XOR 1 with 0, you get 1. You XOR 1 with 1, you get 0. Okay. Now our problem is how do we find s? Now if you want to solve this problem classically, okay, let's analyze the classical case. The worst case scenario happens when s string is some string full of zeros. Okay, in this case each fx is going to be mapped to x itself. Okay, so I mean there won't be any 2-to-1 correspondence. Each bit string will be mapped to some different bit string or the same one, but it's going to be a one-to-one function. So to figure out whether this is a one-to-one or a two-to-one function, you need to check at least half of the inputs and one additional more. So the complexity of your algorithm, or in other words the number of times you need to use this oracle, is exponential on the input size. Alright, now Simon's algorithm, however, is a quantum algorithm, and it's actually the first quantum algorithm that is exponentially faster than a classical one. So let me quickly go over the algorithm part for your convenience. Now in the algorithm, like the circuit definition for it is basically, I mean, these are like the first n bits, I will call them the first register, and these are the last n bits, I will call them the second register. These are the ancilla qubits. Now the circuit goes as we basically put a Hadamard gate to each qubit, superposing each bit string. Okay, then you apply your oracle, then again you apply a Hadamard transformation and you measure. So depending on your measurement result, you will see what s was. That's the key idea, right? So this basically traces the computation. So you just put them into superposition, nothing fancy, just the definition of Hadamard gate. Now you apply the query function. Remember the query function did like on the second register, if this register was xy, it put on the second register y XOR fx. Well, if y is full of zeros, 0, 0, 0 XOR with some binary string is that binary string. So in this case, this query function returns sxfx. Now note that this is a superposition. Like at this point, this is a superposition. So let's say, hypothetically, that we measure this circuit right here, and we get some specific bit string, right, as a result, like some specific result, fx. Now there are, we are told, two distinct states, x and y, that yield that value, right? So after doing that measurement, this state, like state of these first registers, will collapse to this, a superposition, equal superposition of x, y, both of which yield fx. Okay? Now let's see what happens when you apply an Hadamard gate to this state. We just again apply the definition of the Hadamard gate and we obtain this. Now for each z, like for each bit string, for each state, what do we have? We have -1 to the x dot z, -1 to the y dot z, right? Now if x dot z, like if and y dot z are different than each other, okay, then this is +1 and this is -1, or vice versa, and the coefficient for that z is 0. So there's no way that we're going to measure that. So the z's that we are going to measure in the first registers, okay, are the ones for which x dot z is equal to y dot z. right? Like writing y as x XOR s and doing a little bit of arithmetic. What do we have? We have s dot z is equal to 0. So this means like every time we run the circuit, the bit string that we're going to measure here is a bit string that is going to be orthogonal to s, right? Now, if we run the circuit, let's say n times, and we get n distinct n distinct bit strings, n different z's, this gives us a system of linear equations, right? S dot z1 is equal to 0, etc. And we can solve it classically and easily and find out what s is, right? So instead of using this oracle 2 to the n times exponential, we just need to use it in linear time. Okay. Now we've cleared that out of the way. Let's go on to the actual algorithm and actually what we need to cover in this lecture. Okay, I just write down here what do we need to do, but it basically describes this circuit. Okay, let's get to the Qiskit. Okay, in oracles.py, I've also defined the oracle functions for Simon's problem and some additional functions. So let's run this and import those functions. We also need to import the necessary things from Qiskit module. Okay, you actually don't need to insert quantum register or classical register every time. You can just actually just create a quantum circuit by giving an integer as its argument. You can initialize a quantum circuit as such. Okay. Now, okay, what we want to do is apply this circuit. What do we need to do? We need to apply Hadamard gates to first n qubits. Okay, that's what it does. Before we move on, there's actually a more compact way of writing this for function. If you just write qc.h and give argument as a list, it basically applies this Hadamard gate to each index that's in this list. Alright? So this is actually equivalent to appending a gate and giving a list of qubits to it, right? Remember, we use this in the definition of like oracles for Deutsch and Deutsch-Jose, right? This is a very useful thing to notice. So instead of writing this for function, we might as well write this. Okay. Now, after we've done it, we need to apply our oracle function. Okay, it's defined as Simon oracle. It takes in, like as usual, a quantum circuit and the size of the circuit, like n. Okay, and it returns the secret string that it's producing. Okay, we put a barrier and etc. and just apply the Hadamard gates again to the first n qubits and measure everything that we've drawn. Measure every qubit. Let me quickly draw our circuit. Well, as you can see, just as the one that we described above. Now, if we execute this and get the results and plot it in a histogram, we got what? 100, 101, 110. Like we got some results, but so what? I mean, what does this mean to us? Unfortunately, it means nothing at this point, because remember, what do we need? We need z's. What are z's? Z's are actually the bit strings that are measured right in these registers, like 0, 10, 1. So actually our z values are 0, 0, like 1, 0, 0, 0, 1, 0, right? These are the bit strings that we measured. Now, in order to make use of these measurement results that we have, we need to do what? For each result that we obtain, okay, notice that this Q3 corresponds to this index, this Q2 corresponds to this index, and etc. We need what? Q0 and Q1, okay? That's the ordering that we need. So if we just flip this and obtain Q0, Q1, Q3, Q4, okay, and just get the first n bits of this bit string, we basically got Z as a result, okay? So this forms an orthogonal set that our S is orthogonal to, okay? So that's basically this code segment does. It defines an empty list, calls it an orthogonal set, and for each bit string in the results.keys, remember that result is a dictionary, and in Python's, like, these are the keys and these are the values. So if you call result.keys, it will return you a list in which there is like 100, 110, and etc. We basically reverse this bit string for each bit string and get the first n elements out of it. And if this is not in our orthogonal set, we just append it to our orthogonal set. Okay. Now after appending this, okay, what do we get as a result? We get 0, 0, and 1, 0. Okay, our s, which is a 2-bit string, is orthogonal to these guys. Well, actually, at this point, what we need to do is like done. Like, that's all quantum thing we need to do. So afterwards, we should solve this set of equations using Simon solver that I've defined. It just takes in an orthogonal set and returns a bit string that is orthogonal to every bit string in this list. Okay, it's a pretty straightforward function. So let's see what this secret bit string is. If we call Simon solver on this set, our bit string turns out to be 0. Now, remember I said when we describe Simon Oracle, it returns actual like secret string that it's producing. So let's print that out, what it is. Oh, it's 0, 1. So it worked correctly. Okay. Let me go over it and just change n to 3 to show you that it really works. Also, this s string is producing itself randomly in the Oracle. So I also have no idea what it is before I run it. Blah blah. For this like 3-qubit state, our s is orthogonal to 0, 0, 0, 1, 1, 1, 0, 1, 0, and 1, 0, 1. If you plug this into Simon solver, wow, our secret bit string was 1, 0, 1. Let's see, is this the actual one? Yay! Okay, it works. You can actually do it with more qubits. But as you increase the circuit size, I mean, the computation time really grows because the exponential. Okay, it works well too.